The title of today's paper is Long-Range Inhibition Synchronizes and Updates Prefrontal Task Activity, published in the Nature, in 2023. Changes in patterns of activity within the medial prefrontal cortex enable rodents, non-human primates and humans to update their behavior to adapt to changes in the environment, for example, during cognitive tasks 1, 2, 3, 4, 5. Parvalbumin-expressing inhibitory neurons in the medial prefrontal cortex are important for learning new strategies during a rule shift task 6, 7, 8. But the circuit interactions that switch prefrontal network dynamics from maintaining to updating task-related patterns of activity remain unknown. Here we describe a mechanism that links parvalbumin-expressing neurons, a new callosal inhibitory connection, and changes in task representations. Whereas nonspecifically inhibiting all callosal projections does not prevent mice from learning rule shifts or disrupt the evolution of activity patterns, selectively inhibiting only callosal projections of parvalbumin-expressing neurons impairs rule shift learning, desynchronizes the gamma-frequency activity that is necessary for learning aid and suppresses the reorganization of prefrontal activity patterns that normally accompanies rule shift learning. This dissociation reveals how callosal parvalbumin-expressing projections switch the operating mode of prefrontal circuits from maintenance to updating by transmitting gamma synchrony and gating the ability of other callosal inputs to maintain previously established neural representations. Thus, callosal projections originating from parvalbumin-expressing neurons represent a key circuit locus for understanding and correcting the deficits in behavioral flexibility and gamma synchrony that have been implicated in schizophrenia and related conditions 9, 10.